Rasmussen from the University of Utah Electrical and Computer Engineering Department, and today I'm going to talk about Laplace. So the goals for today is to understand what Laplace transform means, and then understand the mathematical steps to achieve a Laplace transform. So the first goal is to understand what this means as far as Laplace. So I wanted to go back to a concept that you guys are more familiar with, which is moving from rectangular coordinates to polar coordinates. And the reason why you would do that is to make it easier. So in rectangular form, you typically will add and subtract. And so that makes it very easy. So if I have a plus bj plus c plus dj, then I would just combine the real terms, which would be a plus c, and combine the imaginary terms of b and d, and that would be my resulting rectangular form. And then the same thing with subtraction, I could subtract off those. So I would add the real forms and add the values for the imaginary. So for in the polar form, which is where you have the magnitude r, ej theta, you would use this one to multiply and divide. So multiplying and dividing is going to be way easier than using the rectangular form. So in this example, it would be, if I was to multiply these, I'll call this 1, theta 1, and then r2 ej theta 2, then this is just going to multiply the magnitudes r1 and r2. And then if you remember the property of the exponential, you can add these theta 1 plus theta 2. So you could add the exponents together. And then if you were going to divide, then you could divide these. It's going to be kind of similar. You're going to divide r1 and r2, and the result would be r1 divided by r2 as the magnitude, and then the exponential property is that you would subtract off the bottom phase. And so adding and subtracting is way easier to do in rectangular form. Multiplying and dividing is way easier to do in polar form. And then you have a method of transferring between each one where the r value let me erase this. The r value is related to the magnitude r is related to the rectangular form by a squared plus b squared, square root of that, and theta is related by the inverse tangent of the imaginary part, which is b over a in this case for a plus bj. And then vice versa, you can change back into the rectangular form from the polar. So this concept is what we're now going to look at for what is called Laplace, which is to, instead of rectangular form, we want to move from time domain into the frequency domain. So same kind of concept as that, except for now it's going to be time domain to frequency domain. And let me erase these. So let me erase them. Okay, here we go. So going from the time domain to the frequency domain, we have a way of transforming from one to the other. So what this is called the Laplace. And so in the Laplace, the notation of that L, curly L, and it's the integration from 0 minus, which is right before an event happens, to infinity. And you would take the function in the time domain multiplied by e to the minus st dt and integrate that. And that will change us into the frequency domain. And then going back to, from the frequency domain back to the Laplace, we do an inverse Laplace, which is the curly L inverse of f of s. And so when we're in the frequency, everything is in s terms, and in time, everything is in t terms. And so again, this makes it very easy. Instead of integrating and differentiating in the time domain, what this translates to is algebra as far as adding, subtracting, multiplying, dividing in the frequency domain. So way easier to do add, subtract, multiply, divide versus integration and differentiation. So that same concept is what the Laplace transform does, and these are the ways of changing back and forth, is using integration. The other advantage of using this method is we looked already at phasor domains, so that's very similar, but the phasor doesn't let us see the transient, which is where you, right after like a switch or an event happens, what happens until it gets to steady state. So that's why we want to use the Laplace, which shows us both the transient and the steady state. So it's more advantageous than just the phasor. And so this is kind of a summary of what I was talking about. From the time domain, you have differential equations, and in the S domain, you have algebraic equations. And again, overall, the advantages is now that we can look at complicated inputs. So we could have something more complicated, such as an input signal like this, where we could describe this mathematically. And it is a very complicated input, but we are able to change that into a frequency domain, and we'll go over into how you change that into the next follow-on videos. Once in the differential, or once in the frequency domain, everything becomes algebraic instead of integration and differentiation. The other advantage is that we can have way more complicated circuits. So we, instead of just having a second order, which was 1L and 1C, and we either had to know was it in parallel or a series form, we can have such a circuit like this, where we have each time-dependent element in here adds an order of differentiation. And so in this one, we have 5 elements that are time-dependent, which means we're going to have a 5th order partial differential equation. Not fun to do in the time domain. And so again, that's why we can move to the frequency domain and solve complicated circuits in a much simpler way. Thank you for watching.